Hello children, welcome back. Today we begin second year topics for physics first chapter, electrostatic charges and fields for a quick revision. Okay, remember it is a quick revision only, so I have to tell everything fast. Hope that you are following. Try to listen to that once again when you are watching. Okay, if you are feeling that I'm fast. Okay, no other way, because we have very little time. Within that time we have to revise a lot. This is meant for the students, those who have gone through these topics already. Okay, that's why we do not explain things very slowly. Okay, that will not do anything good to you also. That we know that also. Yes, so here basic properties of electric charge. Electric charge is conservative. It has a conservative property. What do you mean by the conservative property? Conservation of electric charge. That means charge can neither be created nor be destroyed, but it can be transferred from one body to other body. But total charge of an isolated system is a constant. A charged conducting sphere is made in contact with another uncharged conducting sphere. Charges will be shared, so charges transferred. A glass rod when rubbed with a silk. Electrons have been transferred from glass rod to silk, so that silk becomes negative and glass rod becomes positively charged. In that way, charges have been redistributed. That is, the total charge of an isolated system remains constant. Second property, quantization of electric charge. Quantization means the total charge of a body can be written as an integral multiple of basic unit of charge, and that is, in our syllabus, that is an electronic charge. So total charge is Q. If total charge is Q, and if N is the number of excess or deficient electrons, then Q can be written as plus or minus Ne. From that you can find out N as Q divided by E. In 1 coulomb electric charge, 1 coulomb is the SI unit of electric charge, then the number of electrons in excess or in deficiency is 1 divided by 1.6 into 10 power minus 19, that calculation 6.25 into 10 to the power 18. If 6.25 into 10 to the power 18 electrons are in excess, that body is 1 coulomb negatively charged. In deficient, 1 coulomb positively charged. Okay. Then the third property is additive property. If you have a charged sphere with charge Q as plus 1 microcoulomb, you add minus 2 microcoulomb also onto this in the presence of the 1 microcoulomb charge. Then the final charge becomes plus 1 minus 2, that is minus 1 microcoulomb is the new charge. The charge is additive algebraically. You have to see the sign, and the last one, the amount of charge, magnitude of charge, it does not change with the speed of that charge. Charge is a fundamental, charge is a basic parameter. Charge is a derived physical quantity. Electric current is a fundamental physical quantity. Charge is a derived physical quantity, but charge is a basic concept, basic property of material, like mass. But mass varies with the speed. There is a relativistic variation of mass with the speed. Mass of a particle in motion is slightly more than when it is at rest. Mass varies relativistically with speed, but charge does not vary relativistically. That's the fourth property. Charging can be done in many ways. Charging by frictional electricity. When glass rod is rubbed against silk, glass rod assumes positive charge because few of these loosely packed electrons are torn and transferred towards silk by the mechanical action of rubbing. That is, glass rod when rubbed against silk, glass rod transfers some of its electrons, so it assumes positive charge. At the same time, silk gains electrons, so it assumes negative charge. In the direction of the flow of negative charges, there is an increase in mass. So silk will be slightly more massive than before, but very difficult to distinguish the mass difference because electrons are very light. The second one is charging by conduction. It needs two conductors. When a conducting sphere made into contact with another conducting sphere, both are having different potential. They are charged to different potentials. On connecting to one another, charges will transfer from higher potential to lower potential. That is a process of charging by conduction. Now, charging by electrostatic induction. Charging by electrostatic induction. When a charged body is placed near an uncharged conductor. What happens? Equal and opposite charges are accumulated near and equal and same charges accumulated farther. This is the process of electrostatic induction as it is happening in a conductor. In the presence of electric field due to this charge, there will be a redistribution of electric charges in this conductor, due to which negative, equal and opposite charges assumed at the nearer and equal and same charges at farther places. This is called electrostatic induction. Now this uncharged conductor is not electrified because these induced charges are equal and opposite. At the same time, if you connect this conductor to earth through another conducting wire momentarily, the unbound charges will get neutralized. Unbound charges are those charges which are farther. This unbound positive charges will get neutralized, for which earth will send 4 units of electronic charges as per this diagram to neutralize this plus 4e. So plus 4e minus 4e becomes 0. That's why the rest of the minus 4e charge will prevail in this uncharged conductor. That's the way by which it is electrically charged. Now the charge on this conductor has become minus 4e. Okay, now it gains a net charge. If you do not earth or before earthing, the net charge gained by uncharged conductor is still 0. Okay, charges are equal and opposite in a conductor. Induced charges are equal in magnitude and opposite in the conductor. That's the charging by conduction. Charging by induction. So charging by friction, charging by conduction, charging by induction. Charging by conduction needs a potential difference. Charging by induction, for assuming a net charge, you should earth. These are the few important points. Now, gold leaf electroscope is the device used for detecting the presence of electric charge on any charged body, if any. Another application, you can compare relative strengths of electric charges in each of the two charged bodies. Also, you can find out the nature of electric charge in a body, whether positive or negative, using a charged electroscope. You need to have a charged electroscope. You need to have a charged electroscope to know whether that charge is positive or negative. You can electrify that electroscope as mentioned in the previous slide. Now we move on to the basic law of electrostatics, that is Coulomb's law. Coulomb's law applied for two point charges. Coulomb's law applied for 2-point charges. In vacuum, charges are Q1 and Q2 separated by a straight line distance R. Then these two charges are under electrostatic force equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R square. That in vacuum, but in a medium, in another medium, can be written as 1 by 4 pi epsilon 0 epsilon R Q1 Q2 divided by R square. Then F medium divided by F vacuum is equal to F medium by F vacuum is equal to 1 by epsilon R, where epsilon R is the relative permittivity or also called dielectric constant. Epsilon R has no unit, no dimensions. Epsilon R for water is close to 80. Epsilon R for air is close to 1. Vacuum is exactly 1. Air is slightly greater than 1. It tells you, that parameter tells you by what factor the electric interaction reduced by when some medium is introduced in between. In vacuum, if the force is 80 Newton, if you fill the space between these two charges by water, the force becomes 1 Newton because it reduces from 80 to 1 Newton. It becomes 1 by 80. So force becomes 1 by epsilon R. So in vacuum force is F, then in medium is F by epsilon R. That's the thing. So relative permittivity doesn't have unit of dimension. That's Coulomb's law. For force can be applied with more than two charges. There we have to use superposition principle. You have three charges. Q, Q, Q. All the three are equal in magnitude and positive. What is the total sum total of all electrostatic forces acting on this system? The sum total of all electrostatic forces acting on the system would be 0. If only electrostatic forces are acting over this system, each of those charges cannot be at rest. They will be accelerating along radially outward direction such that the centroid is this circumference of circle of increasing radius, whose circumference will be in contact with each of these charges. The equilateral triangle. Equilateral triangle in the centroid center of the circumcircle. That's the radius is perimeter charge. That acceleration will be variable. You have to fix each of these charges so that each of those charges are in equilibrium. We have to stick it. Charges are at rest and is in static equilibrium. Okay. Now sum total of electric force is 0. What is the electrostatic force acting on any one of these charges? Say this charge. The direction of the electrostatic repulsion is this one. Let that force be F. That charge is under repulsion from the other charge also in radially outward direction, because like charges repel, unlike charges attract. This force also will be F. As it is an equilateral triangle, angle between these two force vectors 60 degree. Resultant will be √3 times. Resultant will be √3 times and will be bisecting. Resultant force is √3 times F, and that will be bisecting these two. Net force acting on any one of that charges will be √3 F in magnitude. This is the way by which we apply superposition principle. Like this one also under root 3 of, this one also under root 3 of. Each of that root 3 f's you extrapolate, they will pass through centroid. That's why the sum total of all forces 0, because each of that root 3 f's will be at an angle. This root 3 f and this is one of that root 3 f. What about the other root 3 f? That will be along this line. And angle between each of these root 3 f's will be 120. 120, 120, 120. Forces are of equal magnitude and angle 120. The resultant would be 0. That is why the total force, electrostatic force, total force is 0. Okay, that's Coulomb's law. Okay, so Coulomb's law states that the electrostatic interaction between these two charges, point charges kept in vacuum, found to be proportional to product of the charges and inversely proportional to the square of distance between the two. So the force depends on the medium. That's very important. Medium dependence of the force. That medium should be a homogeneous medium, then only it can be applied directly. Okay. Coulomb's law can be applied for field also. We have learned field due to a point charge. Electric field intensity defined as limit Q tends to 0, limit Q tends to 0, F divided by Q. Limit Q tends to 0. The charge Q should be tending to 0. Then force per that charge is called electric field. Its unit is Newton per Coulomb or volt per meter. Electric field intensity. Intensity of electric field is a vector. So force per charge is field. Field is nothing but force per unit charge. So that field does not depend on that charge. Field only depends on the source charge. You have a source charge capital Q. At a radial distance r, let there be a point P. If the charge is positive, the electric field is directed radially outward. The field whose magnitude is given by 1 by 4 pi epsilon 0 can be written as K. Electrostatic constant K as 9 into 10 to the power 9 into Q divided by radial distance square. KQ by R square. So field is KQ by R square. Field only depends on capital Q. Field due to capital Q alone. If you place one more charge, small q at P, whatever magnitude, the field at that place due to that charge is not defined at all. So field at any point is defined only due to the other charges in the vicinity, not due to a charge placed at that point. That's Coulomb's law. That's the importance of Coulomb's law. So E equal to KQ divided by R square. That's Coulomb's law for field. So what is the formula for field due to a point charge? 1 by 4 pi epsilon 0 Q divided by R square. Field proportional to Q, field proportional to 1 by R square, also field proportional to 1 by epsilon R. That is Coulomb's law for fields. So we have learned Coulomb's law for forces, Coulomb's law for fields. Point charge, field 1 by 4 pi epsilon 0 Q by R square. Many questions have been asked. When distance is doubled, field becomes 1/4. When distance is doubled, field becomes 25%. When distance is doubled, field reduced by a factor of 25%. Field becomes 25%. Field decreases by 75%. You listen to these wordings or sentences because that questions have been asked. Previously, you may make mistakes. Reduced by a factor of means becomes. So when distance is tripled, field becomes 1 by 9. The force field reduced by a factor of 1 by 9. Okay, decreases by 1 minus 1 by 9. That is 8 by 9. That type of questions are still confusing to children even when they have practiced a lot. Okay, so you have to be careful while answering such questions. Only simple questions are used to be asked recently. So field and force for Coulomb's law, that part is very important. Here for field also you can apply superposition principle. What do you mean by principle of superposition for fields or forces? The presence of a third charge does not alter the force between the other two charges. The presence of a third charge. Suppose an equilateral triangle is there and I have two charges Q1 and Q2. The force between Q1 and Q2, force of interaction, electrostatic interaction between Q1 and Q2 is unaffected by the introduction of a third charge Q3. You see that statement type questions also are very important. The force between Q1 and Q2 still remaining same when you bring a charge Q3 there. Force between Q1 and Q2 unaffected by the presence of a third charge Q3. But something else to be told there. The presence of Q3 definitely alters the force on Q1. Presence of Q3 definitely alters the force on Q2. Either magnitude or direction or both, or sometimes both. But magnitude or direction or none is changed between these two Q1 and Q2. Presence of third charge does not alter force between Q1 and Q2, but presence of third charge alters force on Q1. How to justify that? Force on Q1 from the part of Q2 as both are positive, both Q1 and Q2 are positive. The product Q1 Q2 is also positive. That is Q1 into Q2 is greater than 0, positive. So force is repulsive. So that force will be outward direction along this line. Okay. Now third charge Q3 has come. Q3 also exerts that force. So that force is also still F, same charge. But same charge, let all these charges be same. Okay, that I have told earlier. Then only these two can be measured as same. This angle as equilateral triangle 60, then resultant will be along the angle bisector. And that is root 3F. See, the new force is different in both magnitude and direction. Okay. If that angle was 120 degree, both the forces are F, angle is 120, then resultant is also F. Magnitude has not changed, but direction has changed. So either magnitude or direction or both can change due to the presence of third charge. So presence of third charge does not alter force between the other two charges, but force on each charge definitely changes. That's principle of superposition. Okay. That's all about Coulomb's law. For field and force, these are very important. Now, this superposition principle can be easily studied for electric dipoles. Next topic is electric dipole. Electric dipole. What do you mean by an electric dipole? Electric dipole consists of two equal and opposite charges separated by a small distance. The distance is called dipole length. Dipole has no charge. Dipole has no null point. Null point is that point where resultant electric field is 0. In the surrounding space, no regions where resultant field is 0, but charge is 0. It's very interesting that we know field is given by a charged system, right? But dipole is an uncharged system, but still it can give field and nowhere surrounding it field is 0. So dipole has no null point. Dipole has a moment. Moment of the dipole moment is measured as the product of charge and distance between the two charges. That is called dipole length. Dipole length is a vector. Direction of dipole moment is same as that of dipole length. Unit is coulomb meter. Dipole moment is a vector directed from minus q to plus q. Suppose you have charges in the system minus q and plus q. The direction of dipole moment is this one, minus q to plus q. that is measured as the product of any one of those charges in that dipole and dipole length. Okay. Now, field due to dipole. If you have the dipole moment along this line, so that minus q is at the tail and plus q is at the tip. O is the center of the dipole. Let us use this axis of dipole. Axis. You take a point P on the axis of dipole. The resultant field at the point P will be towards right because the moment is towards right. Direction of field along the axis is same as its moment. അപ്പോൾ ആ ഡൈപോളിന്റെ മൊമെന്റിന്റെ ഡയറക്ഷനിലാണ് അതിന്റെ ആക്സിസിലത്തെ ഫീൽഡ് എന്നുള്ളത് അത്ര കൃത്യമായിട്ട് പഠിച്ചിരിക്കണം, മറക്കരുത്, ചോദിക്കും. Field and moment along the axis are in same direction. Suppose the distance measured from center of the dipole to that point is r. Then what is the field along this axis? General formula 1 by 4 pi epsilon 0 2pr divided by r square minus a square all square, where a is half the length of the dipole. Dipole length is 2a. So oil നിന്ന് ക്യൂവിലേക്ക് ഉള്ള ദൂരമാണ് a. R is the distance from center to the point P. Okay, so field along the axis is equal to this one. The general formula for short dipole where R is much greater than a. Short dipole assumption. Then the field along the axis is reduced, and very common formula 1 by 4 pi epsilon 0 2p divided by r cube. We usually teach 2 kp by r cube. It's easy to remember. So field varies 1 by r cube. Distance doubled, field becomes, tell me, distance doubled, field becomes 1 by 8. 1 by 8 means it has become half of 25%, that is 12.5%. It reduced by a factor of 12.5%. That type of questions may be asked. Okay, at a point along the axis of a short electric dipole, the field has been reduced by a factor of 12.5%. Then the distance has become half. Distance halved along the axial distance, along the axial line, field reduced by a factor of 12.5% when distance is doubled. That concept is important. So these things are to be noted. Now, along the angle bisector, you draw the angle bisector to that dipole. Anywhere along the angle bisector, the field is opposite to the moment. Moment is towards right, field is towards left. Also, field bisector is half the field along the axis at same radial distance. Radial distance should be same. Distance from O to the point P1 is same as distance from O to P2, R, and this also R. Field magnitude is halved, but direction is opposite. So field along the axis is along the moment, field along the bisector is opposite to the moment. That things are very important. And that field can be written as E bisector, general formula 1 by 4 pi epsilon 0 P divided by R square plus A square all raised to 3 by 2. And for short dipole, E bisector equal to 1 by 4 pi epsilon 0 P divided by R cube, that is half that of the axial field. Okay, that's all about field due to dipole along the axis and also bisector. You can form general formula for field. For short dipole, R much greater than A. 1 by 4 pi epsilon 0 P divided by R cube into root of 3 cos square theta plus 1. Let this be the distance between the two charges, minus q and plus q. O be the center, Draw a position vector from center onto some other point some other point P1. Let this be the angle theta and R be the position vector. If theta equal to 0, the point P1 stands on the axis. If theta equal to 0, it becomes cos 0, 1, 3 plus 1, 4, 4 root is 2, 2p by r cube. So this can be a general formula for short electric dipole. If theta equal to 90, cos 90 becomes 0, so it gets p by r cube. Theta 60, theta 30, whatever you can find. Refer this diagram also. Okay, it's also important, students note it. Now, what is the total charge on the dipole? 0. What is the null point of dipole? Very important information. Dipole has no null point. Null point is that point where resultant electric field is 0. If two plus q charges are kept close together, plus q and plus q, where does the null point is? It has a null point, which is the middle. Null point is at the middle, exactly at the middle. This is r by 2, this is also r by 2. If one is plus and the other is minus, plus q and minus q, no null point anywhere. If both minus q, still null point is high. If one is plus q1, other is minus q2, charges are of different magnitudes. They are of different sign, plus q1, minus q2. Then you have to see the null point along the axis itself. But outside the charges, close to the charge having smaller magnitude. If you have example minus 2q and plus q, where do you get the null point? Can you answer, students? Draw the line joining. Along the line joining, where? Inside or outside? Inside or outside? If they are of same sign, null point is inside. They are of different sign, null point comes outside. So where the null point comes here? Here the charges are of opposite signs. Charges are of opposite signs. Null point is close to the one having smaller magnitude. Smaller magnitude, you should not see this sign. Smaller magnitude is this, so null point is close to plus 2. Okay. What is the condition for that null point? If this distance is r, this distance is x, and this distance is r, q1 by r1 square equal to q2 by r2 square, that is q by x square equal to 2q divided by r plus x all square. You can find out x. But here, if one is q1 and the other is plus q2, then null point will be close to this. If q2 has modulus less than that of q1, q2 is one which is smaller. That's why null point is close to q2. Let this distance be x, then the rest of the distance is r minus x. Then you say that q1 by r minus x whole square equal to q2 by x square. You can solve for x. This is the way by which you find null point of point charges. Okay. What about a dipole? A dipole has no null point. Okay. A dipole has no null point. But two such dipoles kept together can have null point. So what is the condition? P1 by R1 cube equal to P2 by R2 cube. That's all. P1 by R1 cube. Because field is P by R cube, right? P1 by R1 cube equal to P2 by R2 cube. That's the condition for null point. Now, what happens to that electric dipole when placed in external uniform electric field? What do you mean by uniform electric field? Uniform electric field, how to recognize? You draw tangent to every point. Draw tangent to every point on that field line. Field line is a curve used for characterizing electric field. Field line is a curve drawn in electric field which can characterize electric field. Crowded field lines indicate stronger field. If field lines are less crowded, field lines are not strong, feeble. The direction of electric field intensity at any point is along the tangent drawn to that field line at that point. No two field lines can intersect, because at the point of intersection, two fields can be drawn in two different directions, which is meaningless. Field is a vector, it is unique. Its value at any point is only one single valued function at that point. That's a vector. A vector has a unique property that it can have only one value at one point. But if two field lines are intersecting one another, at the point of intersection you can draw two tangents which wrongly tell you that at the point two fields are there, which is meaningless. Now, how to identify uniform field? Uniform fields are generally parallel, equidistant, unidirectional. But still there can be some confusions. Like, if you draw concentric arcs, field lines are represented by concentric arcs of differing radii. Each of these three curves show field. Tell me whether it is uniform or non-uniform. Equidistant, unidirectional at every point. Unidirectional, if you draw any line like this, at that point fields are in same direction, parallel to one another. Is it uniform or non-uniform? See students, it should be non-uniform. It was a KVPY question. It was a KVPY, I think it is in 2012 KVPY paper. See, these tangents, these all tangents should be in same direction, then only that will be uniform in space and time. Uniform means it should be uniform in space and time. It should not vary with time. It should not vary with space. So that uniform nature should be in space as well as in time. Then every tangents are not showing the same direction. That's why that is non-uniform. But here, you draw tangent to any point, that will be uniform. Okay. Now you place a dipole here with minus q here, plus q here. And the direction of dipole moment vector is from minus q to plus q. The field and moment are at an angle theta. The net force acting on this dipole is 0. But net torque in this picture is not 0. The general formula for net torque is equal to P cross E. That is tau is equal to P E sine theta. That's its magnitude. So dipole experiences no force as the field is uniform. If the field is uniform, dipole experiences no net force. That's why dipole cannot translate. It cannot gain translational kinetic energy. Its center of mass will be at rest, but it will rotate. So it can gain a rotational kinetic energy half I omega square. And the dipole has a tendency to turn clockwise in this picture. Clockwise. So dipole has a clockwise turning effect. So there is a restoring torque which is given by P sine theta. But when theta becomes 0, that torque becomes 0. But due to inertia, it will continue to move overshooting. And it will go up to the same angle theta at the other side. So the process is repeated so that it can oscillate with a time period 2 pi root I by Pe in gravity free space. Neglect gravity. Then time period of small oscillations of a dipole when disturbed from stable equilibrium. Theta 0 is called stable equilibrium. Then it will oscillate for small oscillations about stable equilibrium configuration with the simple harmonic mode of oscillations. 2 pi root I by Pe, where I is the moment of inertia of the dipole. If m is the mass of each of these charges in dipole and a is the half the dipole length, moment of inertia will be m into a square plus m into a square, that is 2 into m into a square. Ma square plus ma square, that is 2 ma square is the moment of inertia. P dipole moment, E external electric field which is uniform. Okay, this is the net torque. That net torque can be equated to I alpha, where alpha is the angular acceleration. That all may be asked. Angular acceleration alpha equal to d omega by dt, all may be asked here. Okay. So dipole in uniform electric field experiences no force, but it experiences a torque. But there can be no torque if theta equal to 0 or n pi. Theta equal to n pi, no torque. In non-uniform field, but dipole may experience a force. In non-uniform electric field, dipole may experience a net force. Okay. If that charges are at locations where fields are having different magnitudes, okay, or same magnitude in different direction, all that many things are there. It is a little bit confusing. Okay. If the field is non-uniform, it is not certain that there is a net force on it. Why? Field may be non-uniform, but at the site where these charges are placed are experienced by equal and opposite forces. The net force should be further 0. So that all conditions should be exactly given. But generally we can say that the chance of getting a non-zero force is less. Zero force is less in the presence of non-uniform electric field. In non-uniform electric field, charge experience, dipole experiences a force, so common. So that's why in NCERT it is written. In non-uniform electric field, dipole experiences a force. If so, then let us write down the equation for it. F is equal to P dE by dr. This is the formula. F is equal to P dE by dr. From that we can find out the x component of the force, which is P dE by dx, y component of force, which is P dE by dy, z component of the force P dE by dz. Like that we can find out the force in non-uniform field. So dipole, when placed in uniform electric field, it doesn't experience any force. That's why it can have only rotational energy. It can gain rotational kinetic energy half I omega square. There is a restoring torque due to which it can oscillate for small oscillations simple harmonically with period 2 pi root I by Pe, omega equal to angular frequency equal to root of Pe by I. Time period 2 pi root I by Pe. Frequency reciprocal of the period. All that may be asked in examinations. Now we'll move on to Gauss's law and charge distributions. We know charges can be distributed continuously in a line, maybe line charge distribution. Lambda is the charge density, linear charge density dq by dl. Surface charge density sigma dq by dA. Volume charge density rho dq by dV. 3 types of charge distributions are there for continuous charge distributions. Gauss's law makes use of this. Gauss's law states that the sum total of total electric flux closed integral E dot ds through a closed surface, through any closed surface, total electric flux, outward or inward, net electric flux, sum total of outward and inward electric fluxes, sum total, net electric flux, through any closed surface can be easily measured by 1 by epsilon 0 times the total enclosed charge inside that closed surface. Closed surface of whatever shape, no, doesn't matter. Shape of the surface does not matter. That surface is called Gaussian surface. Gaussian surface. A point charge has got a spherically symmetric electric field. Spherically symmetric electric field. Due to which you can choose a spherically symmetric Gaussian surface. Therefore, what is the flux charge enclosed by epsilon 0? That will be giving the total electric flux. So Gauss's law makes use of a path for finding field from flux. First you find flux, then you find field. For finding field, from that you need symmetry. You need to have a spherical Gaussian surface for finding field, but not for flux. For example, you have a charge Q. You have a concentric sphere where charge is at the center of that sphere. The sphere of radius R. What is the total flux? Total electric flux is equal to Q by epsilon 0 if that is in vacuum. If in medium, of course, Q by epsilon 0 epsilon R. Flux reduced by a factor of 1 by epsilon R in that medium. But here in vacuum it is Q by epsilon 0 because Q is the only enclosed charge. That's a total flux. Now you move this slightly here anywhere, keeping that charge inside. Charge Q is still inside, but you are moving this sphere somewhere. The flux remains same. Flux remains same. But if you consider that point at the surface, field at every point are different in magnitude as well as direction. Field is different in magnitude as well as direction. Okay, but when you apply Gauss's law, normally we choose a symmetric surface whose magnitudes of electric field at the surface are to be same. Magnitudes are same because that radial distance is same. 1 by 4 pi epsilon 0 Q by R square is the field at the outer surface. But their directions are different. No concern about that. Magnitude should be same. Field should have same magnitude at the Gaussian surface. While finding the field, otherwise field would be different. That's why. But while finding flux, there is no concern. Okay, because there you should not alter the charge enclosed. Okay, another important feature of this one is you consider a hemisphere. Consider a hemisphere at the open mouth center. A charge Q is placed. In the open mouth, it's an open mouth hemisphere, open mouth, hemispherical bowl, open mouth, center of which there is a charge Q. What is the total flux? We cannot find total flux using Gauss's law as the spherical surface, as the surface is not closed, it is an open surface. So you go for closing it. You cannot take a plate and close it because that is not symmetric. There we need symmetry. Now you find a symmetric surface for closing it, another identical half sphere, then it is closed. Then what is the total flux? That is Q by epsilon 0. But we need to find the flux through only half the portion. That is exactly half, Q by 2 epsilon 0. So flux through the hemisphere is Q by 2 epsilon 0. This was asked in recently JEE advanced paper. So flux through that half sphere is Q by 2 epsilon 0. That's Gauss's law. Okay. Now Gauss's law can be used for finding the field due to an infinite line charge. Infinite line charge is infinitely long, having line charge density lambda, let that charge density be plus positive and charge density is plus lambda. When you try to find out the field at a radial distance r, direction of the field is normal to the wire. That field as per Gauss's law, choosing an imaginary Gaussian cylinder. Gaussian cylinder. Find a Gaussian cylinder. Gaussian cylinder. That Gaussian cylinder looks like this. It has symmetric Gaussian cylinder. Cylinder is of length L. Total length of the charge is infinity. The field is lambda divided by 2 pi epsilon 0 r. And you can see field proportional to 1 by r, but field proportional to length raised to 0. Field does not depend on the length. Field is constant or variable? Variable, because it varies with the distance inversely. Rectangular hyperbola, field distance graph is a rectangular hyperbola. But field does not depend on its length of the Gaussian cylinder. What about the flux? What is the flux? Total flux? Total flux is equal to charge enclosed by epsilon 0. 1 by epsilon 0 times charge enclosed. What is the enclosed charge? Lambda is the line charge density and L is the length. So charge per unit length into length, lambda into length. So lambda L by epsilon 0 is the total flux. See, flux is proportional to length. That's very important. Flux proportional to length, but field independent of length. This will be tested. This is the way by which questions have been asked these days for examinations. Basic theory is to be thorough. The basic concept should be thorough. Phi proportional to L, but field does not depend on L. Matrix type, statement type, assertion reason type, okay, multiple choice. Anywhere this can be, paragraph type, anywhere it can be asked. This concept is very important. So flux and field, carefully you have to deal. While finding flux, it is the best method to use Gauss's law. Okay, in Gauss's law, first we find flux, then field. As per Coulomb's law, first we find field, then we can find flux. Whatever, both true. Gauss's law and Coulomb's law are exactly same. In Coulomb's law, there is an inverse square law. This Gauss's law also carries that information there. Hidden, but it is hidden. That Gaussian surface, it should be symmetric while finding the field. Okay, the shape of that Gaussian surface doesn't matter if you find flux. If you place a point charge at the middle of a cube, the total flux is q by epsilon 0 through the 6 faces of the sphere, of the cube. But flux through any one face will be exactly 1/6 of the total. That is 1 by 6 times q by epsilon 0. That is q by 6 epsilon 0. 1/6. Okay, total flux divided by 6 will be the flux through each face. Okay, but if the charge is slightly moved from center to one side, the total flux does not change, but flux through each faces changes. Where we need symmetry while finding flux through each faces. But flux, total flux for finding that does not change, flux through each face changes. See, these type of questions have been asked. So basic theory is important. You think over that and write somewhere. If any doubt, you can clarify. This is the method. Another one, application of Gauss's law, infinite sheet of charge. Infinite sheet having surface charge density plus sigma. The field at any point does not depend on distance. Field equal to sigma by 2 epsilon 0. Field due to infinite sheet of charge. That sheet only carries charges distributed uniformly over one surface. And the field, it does not depend on the radial distance. Field depends on distance field proportional to r raised to 0. Now you imagine a cylinder. Imagine a cylindrical surface like this, a Gaussian cylinder. What is the flux through this cylinder? The curved surface does not have any flux because field is normal to the cross sections. So this area, let it be A. This area, let it be A. Then the field lines cross normally that area alone. Curved surface, no flux. Then what is the total flux? Total flux is equal to charge enclosed. What is charge enclosed? Sigma A. A is the area of this surface over which charge is spread. Sigma is the charge per unit area, A is the area. So charge divided by epsilon 0. What is the flux? Charge enclosed by epsilon 0. See that flux depends on area. Flux depends on that area. But field, that does not depend on that area. Field does not depend on that area. Charge depends on area. Flux depends on area. These things are very important. This formula very important. Ready-made answer by heart. If it is an insulating sheet, it is sigma by 2 epsilon 0. But if it was a conducting one, charges would have been spread on both sides equally. Then this answer would have been sigma by epsilon 0. That's the general formula for field near the surface of any charged conductor. Field near the surface of any charged conductor is sigma by epsilon 0. So field due to infinite sheet of charge, that is a non-conducting or insulating one, uniformly charged one, that is sigma by 2 epsilon 0. This formula is very important. Another application of Gauss's law is to use this uniformly charged sphere. What do you mean by this uniformly charged sphere? Uniformly charged sphere. Uniformly charged sphere has volume charge density rho. That is the sphere of charge. Because it has charge inside also. A conducting sphere does not have any field inside because there is no enclosed charge. A conducting sphere has no charge inside. Excess charge, if any, in a conductor will reside at the surface, we have learned. That is an electrostatic property of a conductor. But if you make a sphere of charges, that is an insulating sphere. Uniformly charged sphere of radius r. For distances less than radius, that is inside, the field as per Gauss's law, you can find out this rho r by 3 epsilon 0. Field directly proportional to distance r inside. And r greater than r, normal formula can be used as if entire charges are concentrated at the center. You can imagine this charge is to be a point charge. So that entire charge is at the center. 1 by 4 pi epsilon 0 q divided by 1 by 4 pi epsilon 0 q divided by r square. But inside that formula should not be used. Inside, charge enclosed would be different for different concentric spheres. If you imagine a sphere here, charge enclosed is different. If you imagine a sphere here, charge enclosed would be different. And field varies directly with radial distance. So inside field varies radially, outside hyperbolically, 1 by r square. Inside linearly, outside hyperbolically. So this formula is important. So variation of field with distance due to uniformly charged. If you have a charged conducting shell, what is the field inside? Electrostatic shielding that we have learned, very popular concept. A charged conductor with a cavity inside, charged conductor. You have a charged conductor and it has a cavity inside. That cavity carries no charge. Then field inside that cavity is 0. A charged conductor cavity free of charges, field is 0. This is the phenomenon of shielding. Due to this shielding effect only, it is less likely to have an electric shock while being seated in a car, in a closed car, metallic body, field inside is zero. That is electrostatic shielding. Faraday's cage is another illustration, very popular illustration for shielding. Faraday's cage. Okay. Hope that you are clear with this discussion. We have discussed Gauss's law, Coulomb's law, charge distributions, then basic properties of electric charges, methods of electrification, gold-leaf electroscope, also electric dipole, axial field, bisector field, effect of dipole when placed in uniform field and non-uniform field, torque experienced, different applications of Gauss's law, basic concept of Gauss's law, all that. All that include the chapter charges and fields. Okay, hope that you are clear with this. Don't forget to watch this slowly, stop in between and think of this, revise. Then try to read the textbook once, the relevant headings once at least. Then we'll be moving on to the next chapter soon. The next chapter is potential and capacitance. You'll be receiving it soon. Meantime, you go through this. Then we'll stop now. Thank you.